Welcome back to the channel. In this lecture, we will see why just 14 Bravias Lattices. There are many confusions. We will try to break the confusions and get the fact. Here you can see there are different crystal systems and Bravias Lattices. List is given in the table, and you can find that there are number of empty boxes. That means those lattices are not recognized as part of that particular system. Why it is so? That is an interesting fact. We'll try to get the answer today. In the earlier lectures, we have discussed how to define a crystal system, what is the definition of lattice, and what is the conventional unit cell definition of each crystal systems. Here, the defining symmetry of the different crystal system is given. For example, the cubic system is defined by 4 axes of threefold symmetry. That is a defining symmetry for the cubic. Similarly, only one fourfold symmetry for tetragonal and 3 twofold symmetry for orthorhombic and one hexagonal sixfold symmetry for hexagonal and only one threefold symmetry required to define a rhomboidal and only one twofold symmetry is required to define a monoclinic. For triclinic, there is no defined symmetry, but we should remember that for lattice, the defining symmetry is translation symmetry. So, translation symmetry must be present for triclinic system. Earlier discussion on the different symmetry elements of normal class of cubic system. Here the axis of symmetry, plane of symmetry and center of symmetry is given. So this is for the normal class of cubic system, the symmetry elements, in which the red color which I have given as a 3-fold axis. That means 4 axes of threefold symmetry is defining symmetry for that particular system. Okay, that passes through opposite solid angle to solid angle. So this is a defining symmetry. So all the classes in the cubic system will have, it must have 4 axes of threefold symmetry. So since it's a defining symmetry, it must be present in all the classes of cubic system. Similarly, what we have seen the earlier slide, the same defining symmetry must be there for the respective classes on that particular system. In these lectures, we are going to see why there are empty boxes. For example, we'll take, does this n-center lattice have cubic symmetry? The defining symmetry of cubic system is 4 diagonal axes of threefold symmetry. Just you see in the right side, if I rotate 45 degree and orient that diagonal axis, could you able to see that threefold symmetry of that axis? It's not present. So only twofold symmetry we will get. Because of this reason, we are not able to define a cubic symmetry in this lattice. Hence it's absent. That is a simple definition. One should understand why there are different empty boxes. The empty boxes comes because of the defining symmetry of that particular system is not able to define that particular lattice. Hence it's absent. Okay, here we are getting only twofold symmetry in the cubic system when you defining symmetry axis are positioned. Okay, so we are not able to define a defining symmetry of that cubic system in this n-center lattice. Hence it is not present. Here, what is a misconception about the Bravias lattices? You can see number of videos that the n-center cubic is not present because it resembles the tetragonal primitive. Since a tetragonal primitive is present in the Bravias lattice in the list, so n-center cube is not present. Like that you can see number of videos. That is wrong understanding. Here already as we discussed that characteristic symmetry of cubic system is absent in the n-center lattice. That's what it is absent. It is not like that. For example, the way they explain that if you put the diagonal angles, then the yellow color whatever it's mentioned here, that looks like a primitive tetragonal. You can see A and A equal to B not equal to C. You can see the longer axis of A and A by root 2 is a and B axis. Okay, so in this way people used to define. This is wrong. Here you can see this is a FCC, that means face center cubic, and if you able to construct another lattice from this, you can find like this as what we have drawn in the earlier slide. Similarly, if you do, you will get a body center tetragonal. Okay, but both FCC and body center is present. For a better understanding, I have not marked the front and back face points in this particular picture, but you can see very well that by making a FCC of top and bottom faces, you can make it as a body center tetragonal. If you put the same context of earlier assumption that n center cube can create a primitive tetragonal, that's what it is not present, but here it is not valid. So such definitions and such explanation is not valid because it is not satisfying the lattice defining symmetries. But you can see here the fourfold axis of C axis is fourfold symmetry of C axis is present, very well present in the body center tetragonal. Similarly, you can also see that face center lattice also gives the 4x of threefold symmetry. Because of that, both face center cube as well as the body center tetragonal is present. This is the reason why both are present. So similarly, this explanation valid for all the empty boxes. You can check all the by making different lattices. You can verify whether the defining symmetry is present in the lattice or not. If it is not present, then it is not part of that particular crystal system. So this is one should understand why there are empty boxes.